Brought to you by MyGreen Egypt, green resources for efficient energy.
What's up everybody, and welcome to this first video of our new series of designing a photovoltaic solar inverter. And in this video we'll be experimenting on charging batteries connected in series. And why we went with connecting batteries in series or forming a battery bank of batteries connected in series is because we are intending to implement a solar photovoltaic inverter that aims to output a 5 kilowatt power. And at this amount of power, at let's say a battery bank consists of batteries connected in parallel, each battery is 12 volts, you will require a huge amount of current. And I have this calculator here. In order to calculate the output current of our battery bank, you have to enter the output power and divide it by the voltage, and then you'll get a 416 amps. This is a 416 amps output current of your battery system. If you are going to use batteries connected in series, in parallel, I apologize. And at this amount of current, you will require thick conductors. You will also require the charger to output a lot of current, and that will make you design an inductor that can output this amount of current, which is not practical. So we will go with the series connecting batteries in series solution, and most professional inverter manufacturers are going with that solution, connecting batteries in series. And what we will do in our design, that we will connect 8 batteries, those are 8 batteries in series, and at 8 batteries in series, each one can output 12 volts, so you have 8 times 12 and 96 output voltage. So you can divide the same amount of power, 5,000 watts, over a 96 volts, you'll get 52 amps. 52 amps is much less than 400 and something that we calculated before. And I can design, and everyone can design, a charger that can charge a system of batteries at 52 amps. And also you can design an inverter that can handle an input current of 52 amps to step up the voltage to the level of your utility grid voltage. So what we are going to do, I have connected 4 batteries in series, and I've built a test charging or test charger. And this charger is based on a buck converter that will try to charge those 4 batteries, and the charger will go through each battery charging stage. We've talked about this on a previous video. I will put the link up here and you can review it. We have charged 1 single battery, but now we have to charge 4 in series, and we have to make sure, or the charger have to make sure, that each battery voltage doesn't exceed the amount of voltage of the floating charge voltage, in order not to overcharge any of the batteries. If you are going to do that, and if you're going to continuously charging the batteries at a higher voltage, then you are risking of overcharging each battery, and that will cause your battery to sulfate, and that will lower the expected lifespan of your battery. So you're going to have to enter this stage. So you have to preserve the voltage, the amount of voltage on each battery, not to go over 13.5 volts, which we will test in this experiment. So in the next few moments we will do that. So stay tuned.
Here is the proposed scheme of the charger. We have a simple buck converter, and you have at the input the power transformer that will output 100 volts AC, and then the AC voltage then will be rectified on this bridge, and then it will be converted into approximately 100 volts DC. Then this transistor, this MOSFET transistor, will act as the main switch, sending DC pulses to this filtering inductor, and then the output on this capacitor will equal the output voltage of the charger, analogous to the pulse width modulated signal that is being applied on the gate of this transistor. It's a simple buck converter and is easily implemented using microcontrollers. At the output you have this voltage divider, and then you get the feedback signal that will this feedback signal will represent the output voltage. So you'll feed it back to one of the ADC inputs of the microcontroller, and at this sensing resistor you will get a voltage analogous to the current consumed or synced by the batteries. This is the main controller inside the algorithm of the microcontroller, and you have an inner loop, an error current controller loop, an outer loop. In the inner loop, where you control the current, you have this block which represents this DC to DC converter, the buck converter, and you have an internal PI controller where the current feedback get subtracted from the forcing signal, the applied current signal, and then the error signal get amplified using the PI controller, and then the DC to DC converter will convert this error signal into an output voltage, where the batteries will output the battery's output voltage. Then it will get feedback or fed back to the outer control loop, where you'll subtract the feedback signal, the voltage feedback from the force signal, the V input, and then the error get amplified on the PI controller, and the outer loop will control the inner loop to overall control the current and the voltage of the charger. So in the next So this is our proposed design that we have discussed on the paper. The design is mainly a switch mode buck converter. We're using this transformer to supply the control circuit board with 12 volts, and we're using this big transformer here to supply the power circuit board with 100 volts AC, and then it will get rectified on this bridge rectifier. Then it will be filtered on this big capacitor. The amount of DC voltage on this capacitor is 100 volts DC. So if you don't know what you are doing, don't touch these terminals and don't do this experiment at home. This voltage then will get stepped down using a DC to DC converter, a buck converter, consisted of this MOSFET transistor and this small transistor down here, and then the value will be converted to a smaller one at this filtering capacitor after getting filtered out on this inductor. And then the output value, the output voltage will then be used to charge those 4 batteries, lead acid batteries connected in series. We have on the same on the circuit board this small microcontroller here. This is an Atmel AVR 80 Mega 8 microcontroller. This controller contains the program that have the internal BI controller. This controller is measuring the output voltage of the converter. Also, the controller measures the output current of the converter. So the feedback signals that we talked about before get fed back to this microcontroller, and then it will use it inside this internal loop of controlling of implementing a PI controller. So that's it. That's everything that you need to know about this charger. It's pretty simple and easy to implement if you have some experience in electronics. So let's test it. Here we charge each battery in series. This is the voltmeter that will show the voltage on each battery before connecting the charger. So we have a 12 volt point 3 on the first battery, 12 volt point 2 on the second one, and 12.4 on the third one, 12.2 on the fourth one. So, and we have a total voltage on all of them of 49.6 volts. So here are the batteries connected in series, and the charger will connect the power to the charger. Okay, let's return to the batteries, and we'll measure the voltage on each one of them. So now we'll connect the charger and done it. And we'll measure the total voltage or the net voltage on the 4 batteries altogether. So it is 50.4, 50.5, and we'll measure the voltage on each battery. The first one measuring up for 12.6, the second one for 12.5, the third one 12.6, the fourth one 12.6. So we'll wait till all the batteries are charged and we'll return after 30 minutes. So 30 minutes passed and we have to check the voltage on each battery. Remember that if any battery exceeded, the value of the voltage on any battery's terminals exceeded 13.8 volts, that means that this battery is entering an overcharging situation and we have to cut the power immediately from the charger. So we will measure the voltage, the net voltage on 4 of them. So we have a net voltage of 51.7. We'll measure the voltage on each one of them. We have on the first battery 12.9, on the second one 12.8, on the third one 12.9, and oops, I'm gonna put it somewhere neat. You can see it on the fourth one 12.8. So practically they are the same. So we will return after another half an hour and we'll check it back. Now approximately 1 hour has passed and we have to check the voltage on each battery. So as usual, we'll check the voltage on the 4 batteries connected in series, and you remember that each battery's voltage has not to exceed more than 13.8 volts. So we have programmed the microcontroller to fix the voltage on each battery at the point of 13.5 volts, but there is a tolerance of each battery to to rise to be 13.8, which is the floating value. So we'll check now the net voltage, and we have 53.1 on battery 1 is 13.2, on the second battery 13.1, and on the third 13.2, on the fourth 13.2. We're still in the safe side here, so we will return after another half an hour and we will check it back. There's been an hour and a half since the beginning of this charging procedure, and we'll make the same testing one more time. So the first battery's voltage is 13.7, the second battery's voltage is 13.6, the third one is 13.7, and the fourth one is 13.7. Now the charger is leading the batteries into the phase of overcharging, and this phase will continue until the current will decrease to the point where the charger will detect that the batteries are fully charged, and then it will turn into the phase of floating charge by preserving 13.5 volts on each battery. So we will return back to you after half an hour, so stay tuned. Now the charger has entered its last stage, which is the floating charging stage, preserving each battery at a voltage of 13.5 volts. So we will test each battery's voltage. First one 13.5, the second one 13.5, the third one 13.5, and the fourth one 13.5. So this experiment has succeeded, and in the future we will design a new one that can charge 8 batteries connected in series. There is the same concept will be used. We'll just use a higher MOSFET transistors, and also we alter the design a little bit, and we will add an MPPT functionality to implement that charger to be used in solar photovoltaic inverters. So if you like this video, don't forget to subscribe to our YouTube channel and like our Facebook page, and stay tuned because we are going to create more videos until we reach at the end the final design of our 5 kilowatts solar inverter. So have a good day and bye bye.